Hi everyone. Today's topic is backtesting VaR or value at risk. As a reminder, VaR or value at risk is the maximum loss, the greatest loss that you're expecting for the next trading day at a given confidence level. So in this case, the 99% VaR is the maximum loss that you're expecting over the next one trading day at 99% confidence level, meaning that 99% of the time your losses will not be greater than that VaR number. The other side of the coin is that 1% of the time, your losses will exceed your VAR. Backtesting is a model validation tool that will help us answer the question of whether our VAR behaves in a way that we're expecting it to behave. Uh, the number of losses that actually occur, that actually exceed our VAR, will help us answer that question. If the actual number of losses will be significantly different from expectation, meaning that it will be significantly greater or significantly less than what you were expecting, then we will say that the model is not good and it needs recalibration or it needs some work. If our actual number of exceptions is roughly in line with our expectation, then the model will pass back testing, and we will say that yes, our model is good enough and we will continue working with it, and it will not need too much fine tuning. So back testing is one of the model validation tools that's very handy, along with stress testing and other model validation tools that will tell us if our model is reliable or not. So we will employ what's called the hypothesis test, which we've used a lot in statistics. It's a very old, very common way to test at a given, again, at a given confidence level, which is different from the VAR confidence level, whether our model is good or not. We will be comparing our expected versus actual or observed number of exceptions. And let's get to it, and I will be taking some notes along the way. So our solution, let's just inventorize everything that's given and everything we will need for our calculation. So our confidence level for VAR model itself is 99%. This is the confidence level that was given by the model. So VAR confidence level is a one-tailed confidence level because in VAR, in value at risk, we're only concerned with the losses in the left tail of the distribution, and that's given as 99%. How many trading days in our period? It was 252. The expected number of observations or number of exceptions is 1% of 252. So it's 1 minus the confidence level times the number of trading days. We're expecting approximately 252 times 1 minus the confidence level. In a period of 252 days, we're expecting 2.5 days where our losses will exceed VAR. The actual or observed number of exceptions is 6. That's how many times VAR was actually exceeded given in our problem. Now, like I said, the confidence level for VAR is 99%, but there will be another confidence level for hypothesis test itself, which is different and independent from the confidence level of VAR. The other, let me note it first, hypothesis test confidence level is a two-tailed confidence level, meaning that we want to be sure, 99% sure, 90% sure, 95% sure in our result, in our opinion of the VAR model. This is a different confidence level. It can be the same level, but I'll pick a different number, let's say 95%, to avoid confusion and to show that this confidence level is truly independent of the VAR confidence level. And the reason I'm taking these notes is because it will be useful when we work with Z-scores at the two different confidence levels later on. So let me define my null and alternate hypotheses for the hypothesis test. Our null hypothesis, or H0, also known as H0, is that our model is good. We don't have sufficient evidence to prove that our model is bad. So we cannot prove that our backtesting cannot prove that our VaR model is bad. So observed number of exceptions is not significantly different from expected number of exceptions. Remember, we're comparing expected with the actual. So observed number of exceptions is not significantly different from the expected number of exceptions. In this case, our model would pass backtesting. The alternate hypothesis is when we do have enough evidence to prove that our model is bad by means of saying that our actual number of exceptions is significantly different from the expected number of exceptions. So observed number of exceptions is significantly different from the expected number of exceptions. So a model would fail backtesting, and we would need to recalibrate it or change it or revisit the definition. Let me just put an S here. So we will use the approach known as the normal approximation to binomial. So we will work with z-scores because they're typically easier to work with, and for for a large sample size, it works pretty well. So we need to find out what our critical z-score is, what our acceptance and rejection regions are, and we will calculate our actual observed calculated z-score and compare it with the acceptance and rejection region. So before we go there, let me bring in the standard normal distribution, and it will help us locate the z-scores and probabilities that we will need. This is the standard normal table that converts the probabilities in the tail of the normal distribution to the appropriate z-score. Some of you may have seen it before, some of you may have a different version of it, but they all produce the same results if you use them properly. So for our hypothesis test, we're interested in the 95% confidence for a two-tailed test, meaning that two tails together will comprise 5% probability. And we will need to find the z-scores associated with that acceptance or rejection region. So if our calculated z-score falls in the tails, we will reject the null. If our calculated z-score falls within the allowable acceptance region, we will not reject the null, and we will pass the back testing. So how do we find that critical z-score needed for our acceptance region? So first of all, what is the probability of each tail? For a 5% total probability across two tails, probability of each tail is half of that. So one tail probability is half of the 5%. So it's 1 minus the 95%, 1 minus the 95% divided by 2 because we have two tails. So each tail will have 2.5% probability. What is the critical z-score associated with that probability? Let me first use Excel, and then I will show you how to use the standard normal table to find the same number, because you don't always have Excel next to you. Sometimes you have to do it on a paper-based test with a calculator and a table. So you can use the norm.s.inv, which is the inverse of the standard normal, for a given probability. So the z-score, critical z, associated with a probability of 2.5% is negative 1.96. But remember, there are two tails. So there will be one tail on the left, and there will be another cutoff point for the tail on the right. So if we use the negative of that number, we will get the other z-score. Why was I able to use the negative of this number? Is because we know that normal distribution is symmetric. The right side is the mirror image of the left side. So how do we find this 1.96 z-score in the table itself? So we know that our tail needs to have 2.5% probability. So the 2.5% probability needs to be located in the body of this table right here. So 2.5% is right here. 2.5% is the probability of the tail, and the associated z-score is negative 1.9 plus 0.06, which is negative 1.96, the same exact z-score that we got using Excel. So that is our critical z. Our acceptance region is between negative 1.96 and positive 1.96. If our calculated z-score falls outside of this region, then it will tell us that we have sufficient evidence to conclude that our model is bad. Our actual number of exceptions is too far away from expectations. So let me spell out my decision rule here. Decision rule will be if calculated z-score is within the acceptance region, which is the between negative 1.96 and positive 1.96, then we don't have enough evidence to reject. So then do not reject H naught. If calculated z-score is outside of the rejection region, meaning it's greater than the positive 1.96, or if z-score is less than the negative 1.96, then we reject our H naught and we conclude that the alternate hypothesis is true. HA is true. So what is our formula for the calculated z-score? Now we know our decision rule. The calculated z-score using the normal approximation to binomial. Let me bring in the formula that I have saved. Is this. Is x minus pt divided by square root of p times 1 minus p times t. Is approximately normally distributed with a mean of 0 and standard deviation of 1. So let's define what's x, what's p, what's t, and so on and so forth. So x is the actual number of exceptions. P is the probability of our success rate, meaning what is the probability of observing an exceptions if the model was true. And T is the number of trading days in our time period. So let me denote some of these. So the observed number of exceptions is X. And we know that was 6 because that was given by the problem before. So that's the observed or actual number of exceptions. Our tail probability, which is the lowercase p, is given by the probability of the VaR model itself, we had a 95% VAR. So tail probability of the VAR model is 1 minus 99% or 1%. So let me just say model tail probability, which is the lowercase p in this formula right here, is 1 minus the 99% confidence level for VAR itself, which is 1%. Uppercase T is the number of trading days, and that was given as 252 number of trading days. We should have everything to calculate our z-score here. So the numerator and the denominator will have the inputs from these three values. So the numerator is x minus p times t. So it's the 6 minus probability of 1% times the number of trading days. The denominator will be a square root of p, which is 1%, times 1 minus p, which is 99%, times the number of trading days, which is 252. So it's 1.579. So the calculated z-score will be numerator divided by the denominator, which is 2.203. That's our calculated z-score. And what was our critical z? Our critical z was between negative 0.196 and 1.96. I think I misspoke there. So our acceptance region was between negative 1.96 and positive 1.96. And we need to compare our calculated z-score to that acceptance region. So our decision is our 2.2 calculated z-score is outside of the acceptance region. So we reject the null hypotheses, reject H naught, and we conclude that our model is bad. We just failed backtesting. So our model failed backtesting. So it means that the 6 exceptions that we observed is significantly different from the 2.5 that we were expecting. Another very useful tool from hypothesis testing is p-value. So this decision is binary. It just tells us whether our model is good or bad. P-value can tell us a little bit more about it, about our decision. How strong is the decision? How strong is the evidence against H naught? So before we get there, so let's just remind ourselves that our hypothesis test is two-tailed. So there are two tails, and our question with the p-value is, what is the probability of observing this value, 2.2, or what is the probability of observing 6 exceptions given that our model is correct? Given that H naught is true, what is the probability of observing a number as extreme as this, right? And p-value will help us answer that question. So the observed tail probability is the probability of observing 2.2, a value as extreme as 2.2, given that our null hypothesis is true. So let me use Excel first, and then I will show you how to use the table again. So 2.2 is the z-score. What is the probability associated with that z-score? So it's the norm time dot s dot dist, the normal distribution of the z-score uh, cumulative. So actually it's minus C42. The reason why I used negative of the 2.203 is because I'm interested in the probability in the left tail. So if our observed z-score was negative 0.2, what is the probability of that left tail of observing a value as extreme of 2.2? So again, our uh, hypothesis test is a two-tailed test. So the p-value will be the result of the sum of both tails. So p-value of the two tails is double of this value right here. So each tail will have a probability of 1.38%. The total p-value is 2.76%. Let me show you how to find this 0.0138 using the standard normal table. So our calculated z is 2.2. What is the probability of observing a value as extreme as 2.2 if the model were true? So negative 2.20, the associated probability is 0.0139, meaning which is very similar to what we got using Excel. What is the interpretation of p-value? So the rule of thumb is that the lower your p-value, the more confident you are in rejecting your null hypotheses. So a p-value of close to zero means that you have a very strong evidence to conclude that your null hypothesis is false. Uh, you compare your p-value, which is 2.7%, to your significance level of the test itself. In our case, we had a 95% hypothesis test confidence level. Our p-value is smaller than the 5%, so our decision is the same. We reject the null and we fail backtesting. So the decision based on the p-value is the same as the decision based on the calculated z-score and the decision rule we set out earlier. So what does it mean in this case? The 6 days where our losses exceeded our estimated VaR for that day is too much. This is too high of a number. The dispersion or the divergence of our observation is too high. We're too far away from our expectations, so backtesting fails. We need to do something with our VaR model to either recalibrate it or revisit the definition of the VaR. If we used a normal distribution assumption in our parametric VaR model, maybe it makes sense to pick a different distribution, or maybe it makes sense to use a historical simulation approach instead and see if it works better. So hopefully this was useful, and thank you for watching.